In this video, we're going to review engineering stress by looking at topics of tensors, principal stresses, including a quick matrix algebra review. We'll discuss eigenvalues, their importance, and how to derive them, and equations to generate eigenvalues. We'll briefly look at the simplified 2D stress case, and then we'll have some useful MATLAB and do a few examples. So when we think about tensors, the first thing is to give a definition. The definition of a tensor is a geometric expression of space. And there's different types of tensors. You're probably already very familiar with many common tensors. For instance, a zeroth order tensor is nothing but a scalar. So for instance, mass. If you say you have something weighs or has a mass of 5 kilograms, you are expressing a zeroth order tensor. A first order tensor would be something like a vector, so for instance velocity or force. And now as we express it, we're expressing not just a value but also a value and direction. Geometrically, we're now considering something like an arrow. It's pointing from one point to another point, and it's expressing a value as well as a direction. For a second order tensor, it's not quite as visually obvious. And so what I'm going to say for generalization is that it's a special matrix. And what I mean by that is all tensors can be expressed, all second order tensors can be expressed as a matrix. But not all matrices are tensors. There are only special matrices that are tensors. We use two of them in mechanical engineering fairly regularly. One of them is a rotational matrix, and I'll give an example of that in just a second. And the other one is the stress tensor, and that's what we're really going to be discussing today. The rotational matrix, if you notice, each of the directions are, each of the vectors here that compose the matrix are orthogonal to each other and have a unit, each of them are unit vectors, and that's some of the definition, not the complete definition of what a rotational matrix is. But there's some special features of the way these work, and that's what we're going to consider. So the best way for us to visualize the stress tensor is to think about the stress cube. So we know that stress has units of force per unit area. We know that when we're considering stress, we're considering an infinitely small cube, and this notation is probably familiar to you, where you have normal stresses located on the diagonal here and shear stresses located on the off diagonals, and it's an important enough concept that we even give it a different symbol. So sigma represents the normal stress while tau represents the shear stresses. And as a reminder for the subscripts, the first value has to do with the plane on which we're discussing. The second value has to do with the direction of that particular stress value. So xx is on the plane of the x in the x direction, and xy is on the plane of the x and in the y direction. And notice, because this is infinitesimally small, we have some repetition. In other words, tau yx is going to be equal to tau xy. It's just the way it's going to have to work out physically. This cube here is a physical cube, and its movements have to work out with each other. They have to be symmetric. So that means that although there are 9 values in this matrix, there's really only 6 unique values. We have our 3 orthogonal, or our 3 diagonal values that are the normal stresses. Those are unique. And then tau xy is going to be equal to tau yx by definition of the physical space. Tau xz will be equal to tau zx. And so the off diagonals are repeating, and so only 6 values are needed to define the stress tensor. Okay, so with that as a reminder of what the stress tensor is and what we're trying to do, let's talk a little bit now about the orientation of this cube. Remember, this cube is infinitesimally small, And the reason that I've chose x to be in this direction is really, some cases, somewhat arbitrary. So in other words, there was nothing having to do with the loading condition that determined my coordinate system. And so it might be convenient for me to restructure my coordinate systems to a way that matches the loading condition. And what I'm really trying to do is get this diagonal, get those diagonal values, the normal values, to be as high as possible. Okay? And it turns out that with any stress cube, so with any stress condition that we have on an infinitesimally small piece of a part, we can always reorient our coordinate systems so that the diagonals become principal stresses, the maximum that they can be, and all of the off diagonals are equal to 0. So what we're saying is that we have this 6 values expressed in a 9-value matrix. What we want to do is, by reorienting x, y, and z, we want to reduce the off diagonal to 0. So to be able to accomplish that, we're going to have to dive into a little bit of matrix algebra. So let's do a quick review of some matrix algebra principles. The first principle is that two matrices multiplied together, the order matters. So A times B is not equal to B times A. Hopefully you remember that. Let's say R is a rotational matrix. Here's some principles about rotational matrices. The transpose is equal to the inverse. The determinant is equal to 1. And it's composed of unit vectors, and the definition of a unit vector is the square root of the sum of the squares of the elements of the vector is equal to 1. Okay. We also know that vectors are orthogonal if their cross product is equal to 0. And by orthogonal in 3D space, we're typically meaning 90 degrees out of phase. But this statement that vectors are orthogonal goes well beyond our three-dimensional matrices that we use. Okay, so here's what we have. Here's what we want to have. What can we do to reorient a new x, y, and z such that we now have off-diagonal terms that are equal to 0? So let's create a unit vector, and let's just say that it's pointed along an important direction. I don't know what that direction is yet. I just know that there has to be one that exists. Okay, so I'm going to express this as ui. And then I'm going to say that there's a rotational matrix that's composed of 3 unit vectors, u1, u2, u3. So if I wrote it all out, it would look like this. Okay, so there's 9 values, 3 unit vectors, and these are expressing 3 important directions, and those important directions are orthogonal to each other. Okay? Okay. This is a claim I'm making, and I'm not going to prove it. I'm going to demonstrate that it works, but it's not going to be quite a formal proof. And so what I'm saying is that if I understand where the important directions are, I have the necessary building blocks to transform where the stress state that I have expressed it, the element is currently expressed in, with a stress state. It's the same stress state, but now it's expressed in terms of principal stresses. Okay. So let's work through this derivation. First thing I'm going to do is, starting with this as a fact, and again, just trust me that this is true, I'm going to pre-multiply both sides by the matrix R. We know that R times R transpose is equal to unity, so that reduces to I, and then I'll just, since it's unity, we'll just remove it, and then expanding this desired matrix, this sigma prime, into 3 different values. I'm now going to recognize that this is the same as I times a vector of sigma 1, sigma 2, and sigma 3. One of the very few matrices that can move around freely is the unit vector. So it turns out that I times R is equal to R times I, so rearranging and then dropping, and this R should still be bold. And then let's call this matrix, or this vector right here, sigma bar. Let it represent the expression of sigma 1, sigma 2, and sigma 3. Okay, so reducing, what I have is this first term is equal to this last term. Now notice what we've done. This is a vector. This is a matrix. This is a vector. So now I'm going to recognize that R is composed of 3 unit vectors, and it turns out that if I consider the vectors independently, so if I just consider u11, u21, u13, this unit vector right here, I can express that there's actually 3 of these. Sigma times u1 is equal to sigma 1 u1. Sigma times u2 is equal to sigma 2 u2. And sigma times u3 is equal to sigma 3 u3. I can also rewrite this final statement by subtracting both sides of the equation by this term and calling this new matrix sigma minus I sigma I. We're going to call that A, and that's setting it equal to 0. So now I have this new matrix that's composed of sigma minus I sigma I times some vector is equal to 0. Now, this is only going to be true for an arbitrary UI if the determinant of A is equal to 0. So that's what our next job is, to figure out how to get the determinant of A equal to 0. So there's A written out again. This is substituting in for A for particular sigma 1 or sigma 2 or sigma 3. So I can do this 3 different times. And when I do this, it becomes kind of a nasty, kind of a nasty set of equations. We're going to get this sigma to the 3rd minus some constant c squared minus another constant times sigma times another constant. That's equal to 0. That's because I'm taking the determinant of this matrix. Working out the math, we can actually calculate what C1, C2, and C0 are equal to. And again, they're fairly complex, but it's a very simple thing to read off the original values into these values. And noticing a notation change, notice that my sigma xx is equal to sigma x in the constants here. This is a 3rd order equation, and so really what we're doing is we're finding the zeros of this 3rd order equation. Now, this is fine to do. You probably still want to use a calculator if you do this by hand, but the way that I would prefer to do it is to go into MATLAB and use the Eigen function. So, and I'm going to do an example showing both ways, but the Eigen function of sigma, that's this matrix right here, not A, sigma. Eigen of sigma will produce for me this vector right here at the end, which has the principal values, and these are what we call eigenvalues. And the whole notion of what an eigenvalue is exactly, it is the part that best expresses the maximum values of the matrix. So given a given stress state, oriented in the way that is most likely to, that creates the greatest normal stresses, and those values on the diagonal are the eigenvalues. And incidentally, the vectors used to create those eigenvalues is what we know as eigenvectors. Okay, very often we'll do this in 2D. So there's a lot of cases where the 3rd dimension is equal to 0. So if there's no stress, our bottom row and 3rd column of all of the matrices are equal to 0, and it simplifies into just a 2 by 2. So let's look at a 2 by 2 and calculate it by hand. So for example, let's say we have this stress state, and this probably should have some sort of units associated. Let's say PSI, pounds per square inch. Okay, so this is the infinitesimal stress state of an x and y coordinate system. And what I want to know is what is the maximum stress in the normal direction at this location with this stress state. So what we're doing is we're going to take the determinant of A, where A is defined as this sigma that I've defined here minus some sigma I, and we're going to set it equal to 0. Okay, so I'm just going to subtract sigma off the diagonal terms. And then the determinant we find by multiplying these two terms together and then subtract these two terms multiplied. So let's see what that looks like. These two terms, I've got 7 minus sigma times 5 minus sigma. I should get 35 minus 12 sigma minus sigma squared. Then minus negative square root of 3 times negative square root of 3 is positive 3. And then minus that is minus 3. So there's the determinant worked out. Now I can solve and reduce, and we get a simple solution of 8 and 4. We'll talk a little bit more about the order that I put these values in. Notice the way I'm putting it is sigma 1 has the maximum value and sigma 2 has the minimum value. So I'm always going to rank them from maximum to minimum. Okay. Now, let's take a look at how we would do this in MATLAB. I'm going to pull up the MATLAB window. I've already set some values in here, so let's see what I've put in for sigma. Okay. If you look at the problem, we have 7 and 5 on the diagonals and minus the square root of 3 on the off diagonals. So that's what sigma is. And what I'm going to do is I'm going to say that sig bar is equal to Eig of sigma. Notice that although we got the same answer, there's 4 and 8, MATLAB is always going to give the minimum first and move up to the maximum. So as you give answers to me, always switch the values of what MATLAB gives you so that you're giving me the maximum first. Your principal stress is the highest stress, and in that case, in our case, it's 8. Okay. Let's do another example. This one, to solve by hand, we would need to subtract sigma down the diagonals, find the eigen, find the determinant of this entire matrix minus the sigmas down the diagonals, solve for 0. This would be fairly complicated. We're going to do this again by plugging it straight into MATLAB. So going back to the MATLAB window, let me clear this screen. And let's let sigma equal to check that these values are the ones that we wanted. 45, 2.5, 5 minus 20 minus 1.5, 2.5. Alright, that looks right. So again, sig bar is equal to and there are our eigenvalues. So our principal stress, the highest stress, is going to be 40.5. The minimum stress is going to be minus 20.68.